This is Bob Capetta, and this lesson looks at compound statements and logic. So I have two statements. Remember, they've got to be well defined, and they have to have a truth value of either true or false. P, the dog is sleeping. Q, the cat is eating. So I want to figure out some way to express the following using notation from symbolic logic. The dog is sleeping and the cat is eating. P and Q. So what symbol do I use to represent and? I use a caret. It looks a little bit like an A that's missing its horizontal piece. So that's our symbol in symbolic logic for and. How about the dog is not sleeping and the cat is eating? So not sleeping will require me to negate statement P. So we need to go not P and Q. So we put the tilde in front of the P. That's not P and Q. Unfortunately, my mathematics text editor puts this tilde way to the left of the P, so it looks like maybe you do the and first and then you do the negation afterwards. That is not the case. I really want to emphasize that. Not P and Q is not the same as not P and Q. So to clarify this, you could put parentheses around the not P, and then there's no ambiguity. So it's just kind of some advice. Textbooks don't typically do that, but if you're writing an exam, you might want to put in parentheses to make sure you avoid that problem. How about this one? The dog is sleeping, but the cat is eating. If they are happening simultaneously, then you should think of it as an and. The dog is sleeping, but the cat is eating. The dog is sleeping, yet the cat is eating. These are other examples of simultaneous occurrences. So if that's the case, I read this again as P and Q. P and Q there. All right, let's change up our examples. Almost. Dog is sleeping, yet the cat is not eating. Dog is sleeping, P, yet again, essentially and. Cat is not eating, not Q. P and not Q. Now we're going to go ahead and switch it from and to or. So this says the dog is sleeping or the cat is eating. So we need a symbol in symbolic logic to define or. And we just take this and symbol and flip it upside down so it looks like a V. So that's our symbolic logic piece of notation for or. That's P or Q. Now what does or mean? The dog is sleeping or the cat is eating. Well, when is that true? It's true if the dog is sleeping, sure. It's true if the cat is eating, sure. But is it true if both of them are happening? If the dog is sleeping and the cat is eating, is that a true statement? That becomes tricky because in spoken language, you don't typically think of them both happening simultaneously when you say or. When you say, I'm going to go to Rome or Prague, that doesn't usually imply that you might go to both. But in math, that's exactly what it implies. In mathematics, or means either the first is true, or the second is true, or both are true. So in computer programming, this is sometimes called the inclusive or. But when we use spoken language, when we use the word or, oftentimes it means exclusive. Either one or the other, but not both. But please keep in mind in mathematics class, or means inclusive, one or the other or both. So here's our example. This summer we will travel to Rome. Q is this autumn we will travel to Prague. P and Q means both must happen simultaneously. So if we're going to describe that, write that out in words, what will it be? This summer we will travel to Rome, and this autumn we will travel to Prague. Boom and boom. Good. When is this true? What must be true for an and statement to be true? Both must occur simultaneously. So we must travel to Rome, we must travel to Prague for P and Q to be a true statement. But now we look at the or statement, right? P or Q. So in words, this summer we will travel to Rome, or this autumn we will travel to Prague. In spoken English, oftentimes that means exclusive. You're not really implying that you might do both. But in mathematics, that's exactly what we're saying. At least one must happen. So either I will travel to Rome in the summer, or I will travel to Prague in the autumn, or possibly I'll do both. If I do both, that's still a true statement in the world of mathematics. So please keep that in mind. Okay, our next example. P is the fact that a person has earned a degree in mechanical engineering. Q is the event that a person has studied calculus. P and Q, so we have a person who has earned a degree in mechanical engineering and has studied calculus. So maybe Maria is a person who has done both. If she has a degree in mechanical engineering and she has studied calculus, P and Q is a true statement. But now we're going to introduce this, P arrow Q, sometimes thought of as P implies Q. The simplest way to think of this is if P is true, then Q is true. If P is true, if a person has earned a degree in mechanical engineering, then a person has studied calculus. Does that seem like a reasonable statement to you? If a person has earned a degree in engineering, do you think that person has probably studied calculus? So indeed, more than likely that is true, but we'd have to take a look at the example to determine the truth value of that statement of various individuals. But how about Q implies P? So if Q is true, then P is true. So that's sometimes called the converse of the original statement, P implies Q. If Q is true, then P is true. Does that seem reasonable? If a person has studied calculus, then a person has earned a degree in mechanical engineering. So think of that for a minute. Does that seem reasonable? And I will say no, because I have studied calculus, but I have not earned a degree in mechanical engineering. So one bad case tells me that this statement is not a true statement, at least if I am part of that universal set. Now, how about this one? Not Q implies not P, or if Q is not true, then, remember this is an if-then statement, P is not true. If Q is not true, then P is not true. If Q is not true, if a person has not studied calculus, then P is not true, then a person has not earned a degree in mechanical engineering. Does that sound reasonable? And I think it does, and this is actually called the contrapositive, which again in more advanced courses in logic you can show that that is equivalent to P implies Q. So other ways to just sort of go back and forth, be able to look at the symbols and convert it into words, be able to look at words and convert it into symbols. That's something that students should be focusing on when studying these concepts. All right, our next concept is this notion of if and only if. This causes trouble sometimes, and here is our symbol. P if and only if Q. Now, what does that mean? What does that mean? P is true if and only if Q is true. Let's take a look at our example. We're saying Lazy Joe studies and Lazy Joe has a mathematics exam. P if and only if Q. So essentially the if then goes both ways. Notice the arrows pointing both ways. If Lazy Joe studies, then he has a mathematics exam. So basically he doesn't study for anything else. If he studies, he has a mathematics exam. But it also goes, the arrow points Q to P. So if he has a mathematics exam, then he studies. So recognize this is biconditional, it's going two directions. And that's what the if and only if statement tells us. Again, if Lazy Joe studies, then he has a mathematics exam, and if he has a mathematics exam, then he will study. That's what the if and only if statement means. So he studies if and only if he has a mathematics exam. Now, you may see this notation in some textbooks, IFF, for if and only if. So you might see Lazy Joe studies, IFF, he has a mathematics exam. Although frankly that was more popular years ago than it seems to be currently. Let's look at an example of an if and only if sort of discussion. It is Christmas Day, the city zoo is closed. So I want to look at this from two directions. So we're going to say, if it is Christmas Day, the city zoo is closed. So that's telling me if it's Christmas Day, if P, then Q. If P, then Q, we write this way. P implies Q, P arrow Q. Now, certainly one would think that zoos are closed on Christmas Day. But is that the only day the zoo is closed? Well, maybe. And that's what we're going to say here. If the city zoo is closed, it must be Christmas Day. So in that case, Christmas Day is the only day the zoo is closed. Notice the if it's Christmas Day, the city zoo is closed, and then the zoo is only closed on Christmas Day. There's the if and only if idea. So that tells us if Q is true, then P is true. If P is true, then Q is true, and if Q is true, then P is true. So really, we have these two things, right? If it's Christmas Day, the city zoo is closed, and if the city zoo is closed, it must be Christmas Day. We could write it in symbolic logic this way. If P, then Q, and if Q, then P. But that is what if and only if tells us. These two combinations put together have the arrows pointing both directions, and we say P if and only if Q. That's what that means. But I recognize that's challenging. The notion of if and only if is not necessarily an obvious thing for us to try to understand. Let's take a look at three statements. P tells us a person completes the calculus sequence. Q tells us a person completes a course in electromagnetism. R, a person can enroll in electrical engineering courses. So we want to go ahead and convert from words into symbolic logic. So let's read this carefully. If a person completes the calculus sequence and completes a course in electromagnetism, then the person can enroll in electrical engineering courses. So let's go from our if to our then. Completes a course in calculus sequence, that's P. Completes a course in electromagnetism, that's Q, and there's an and in between. So we see P and Q first before the then. Then the person can enroll in electrical engineering, so P and Q after the if, then R. So if P and Q, then R. How do we write that with symbolic logic? Like this. If P and Q, then R. P and Q in parentheses implies R. If you would take the parentheses off, then it would mean something different. Because the implication, the arrow, has precedence over the and. So again, my advice is use parentheses whenever there's any ambiguity on what the order of operations will be for your symbolic logic. Let's look at another one. If a person completes a calculus sequence or a course in electromagnetism, then the person can enroll in electrical engineering courses. So at this school, they're not requiring both. If you do calculus, that's enough to get into electrical engineering. If you skip calculus, but somehow you did the electromagnetism course, you're saying good enough, you can take our electrical engineering courses. So how do we write this? Again, focus it from the if to the then. If calculus or electromagnetism. If P or Q, then R. If P or Q, then R. How do we write that? If P or Q, then R. P or Q is in parentheses. That's the if part, then R. And again, you need the parentheses here, otherwise you have ambiguity on what the order of operations would be, and the arrow takes precedence over the or. So the parentheses are needed here. Let's take a look at one more. If a person cannot enroll in electrical engineering courses, then either the person did not complete the calculus sequence, or the person did not complete a course in electrical engineering. So if a person cannot enroll in electrical engineering courses. So if cannot enroll electrical, so not R. So if not R, if negation of R, then either, so then, the then tells us that's where the arrow goes. So not R, then either did not complete the calculus sequence, not P, or the person did not complete the course in electromagnetism, not Q. So if not R, so not R implies what? Either not P, either no calculus or no electromagnetism. So again, parentheses are important here. If you didn't have them, it wouldn't be clear in terms of which is done first. And that will conclude this lesson.